Since I'm discombobulated and make that mistake, Sarah Jones, who did her undergrad at Northern Arizona University before coming down to the University of Arizona, she works for the Atlas collaboration, which is part of the Large Hadron Collider at CERN, the big particle accelerator just outside Geneva. And this is the facility that found the God particle, which I'm sure is which is a term that Sarah must hate. And so this is the Higgs boson. This is the particle that's responsible for mass. And Sarah was part of the experiment that did this, and she'll be telling us all about her work to begin with. So, Sarah.
Thank you. Yeah, and thank you all for coming. So, I actually was not involved on the analysis that discovered the Higgs boson, but I am on one of the two experiments that did participate in the discovery. So, yeah, so I'm a PhD student here at the University of Arizona. Can you guys hear me in the back? Am I projecting? Okay, cool. So I do particle physics research. So I work on the Atlas experiment, which is kind of what I'll focus on when I talk about the actual detector. But there are 4 experiments at the Large Hadron Collider. So I'll cover that next. So I just want to give you an overview of kind of how we search for new physics at the Large Hadron Collider and what possibilities still remain. So here's an aerial view of where the Large Hadron Collider is located. It's kind of straddling the border of France and Switzerland. And of course, this is a footprint that's shown on the surface of France and Switzerland. The collider is actually not located on the surface. It is buried underground, about 200 meters, in this tunnel that houses the actual accelerator facilities. And the Large Hadron Collider is the largest particle accelerator in the world. It is approximately 17 miles in circumference, or 27 kilometers in circumference. And along the perimeter of the ring, there are, thank you. Fuel, okay. Along the perimeter of the ring, there are 4 main experiments that search for physics using the collisions that take place in this accelerator. 2 of those experiments are called CMS and Atlas, and these are general purpose physics experiments that, what I mean by general purpose is they use the proton-proton collisions. So we're accelerating protons around this ring, and they use the data from these collisions to basically look for anything new, anything that the universe is willing to throw at us in terms of things that we haven't discovered yet. And then the other 2 experiments are Alice, which I'll pronounce it Alice. It looks like Alice, but if you slur Alice, it sounds like Atlas too much, so I'll use the French pronunciation and say Alice. Alice looks at, they actually use lead-ion collisions instead of proton-proton collisions, and they are essentially studying this, this form of matter called quark-gluon plasma, which was purported to exist right after the Big Bang, when the quarks and gluons were the only things in the universe, and they were in this essentially hot, dense plasma state of matter, and they had so much energy that they couldn't form into atoms yet until the universe expanded and started cooling down. So Alice is trying to essentially create that form of matter with lead-ion collisions. So that's what they're studying. LHCb is studying, is using bottom quarks. That's what the B stands for, or beauty quarks, if you're old school. They're using those particles to study why we live in a universe that is primarily dominated by matter. We don't tend to see clumps of antimatter floating around in the universe, at least in terms of what we can observe right now in the universe. So they're studying why, after the Big Bang, we think matter and antimatter were created in equal amounts, and why right now we're in a matter-dominated universe. Okay, so let me show a short video here that zooms in on what actually happens in these proton-proton collisions. So this is going to focus on these beams of light, which actually look like beams of light, but they're not beams of light. They're representative. They're kind of a simulation to represent the protons. But in reality, we collide 10 to the 11 protons in little bunches together every 50 or 25 nanoseconds, 50 to 25 nanoseconds. So these beams of protons are getting accelerated through various levels of the synchrotrons, and they eventually get injected into the main LHC ring in opposite directions, where they then come to collision at each of these 4 experiments. Now here is a simulation of the tunnel. The blue around the actual accelerator is very high powered magnets that serve to curve the protons into their trajectory into the circle, because they're charged particles. They need a magnetic field in order to curve. And then you see them coming together at the center of these experiments. And this is a simulation that Atlas made to, so it's coming together at the center of Atlas in this particular simulation. And you can see the final states that we see from this. This is an example of a final state. Now, in reality, we tend to see final states that look a lot messier than this. But this is a unique and important final state that was actually used in the discovery of the Higgs boson in 2012. So this is 2 photons in the final state. That's what the green is representing. And I'll get into what the detector looks like, etc. But the green is representing the energy deposited in the detector by photons. And we represent the photon by the letter gamma. So that's why I say proton, proton to gamma, gamma here. So that's what I mean by final state. So, right, so let's zoom in on Atlas. So like I said, I'm on the Atlas experiment. So the majority of this talk, I'm going to focus on Atlas, not the other experiments at the LHC. So here's a picture of the Atlas experiment. And it's the largest of the experiments at the LHC. It's approximately 44 meters in length here, this way. And this is the beam pipe, and proton-proton collisions happen at the center of the Atlas detector. And for scale here, you can kind of see 2 people standing on the muon spectrometer, but in reality, we don't stand on the muon spectrometer. That would be bad. But this is just to show scale. So in general, you can think of an experiment like this surrounding the beam pipe as kind of an onion, a cylindrical onion, so not a spherical one, but where the center of the onion is where the proton-protons come to collision, and the various layers of the onion are designed in such a way to detect different types of particles. And that's why we have so many different layers. So let's imagine slicing the Atlas experiment in half, although not in reality because that's my PhD dissertation, so hopefully we don't do that. But then we take a cross-section of that and take a wedge of that cross-section. So if you can imagine slicing the cylinder in half and then taking a wedge of that, this is what you get. And the center of this white circle down here is where the proton-protons come to collision. And outside of that, we have the inner tracker, which is responsible for providing charged particle tracks that we can trace back to the interaction point. So we only get charged particle tracks in that part of the detector. And the curvature of these charged particle tracks, so you'll notice the proton is curved in a different way than the electron is curved. And that's due to this magnet here, the solenoid magnet. And so we can determine the charge of the particle. Outside of that, we have 2 sets of calorimeters. Calorimetry is basically measuring energy. Calorie means energy. So outside of the magnet, we have the electromagnetic calorimeter. This is where particles that are charged or interact electromagnetically tend to deposit most of their energy. And then outside of that, we have the hadronic calorimeter, which is where hadrons, or composite particles made up of quarks and gluons, tend to deposit most of their energy. Now, in reality, this wedge is just a depiction of kind of how we distinguish between different types of particles, but in reality, the events that actually come from proton-proton collisions are a lot messier than this. So we'll have a lot more particles, and it's a lot harder to distinguish between which particle is which. You'll notice there's a track, this orange track here, that goes all the way out to the outermost parts of the detector. This is the muon spectrometer system, and the reason we have a different detector system on the outer edges of Atlas to detect muons is because muons are essentially 200 times the mass of electrons, but in most ways they're the same except for their mass. But due to that mass and due to the energies that we typically see them, they tend to make it all the way out to the edge part of the detector without interacting much and without depositing a lot of energy in this inner part of the detector. So that's why we have a spectrometer designed specifically to track muons. Then you'll notice these dotted lines here. These represent non-charged particles, so the neutron and the photon are not charged. And then this dotted line here that's going outside the detector is a neutrino. And we cannot directly detect neutrinos. They tend to just not interact with our detector. Our detectors are essentially invisible to neutrinos. And the way that we know, the way that we have to account for them in interactions is by our good old friend from, first Physics 101, conservation of momentum. So if we can imagine protons coming in and colliding in the detector, the net momentum in this direction has to equal all the net momentum going out. So if we tend to see a large spray of particles going in one direction, then we have to infer by conservation of momentum that some particles that just we couldn't detect go in the other direction. So that's essentially how we characterize the presence of neutrinos, and we use the term missing energy, specifically missing transverse energy, but that's transverse to the beamline, to determine the presence of neutrinos. Okay, so that's the wedge, that's the detector. Now, this is a talk about what we can detect in terms of new physics with these detector systems. So what form can new physics take? So let's start with what we know. So in particle physics, this is the standard model, and this is all of the fundamental particles in the universe that we know of right now. So in everyday matter, the table, the beer that you're drinking, you yourselves, everyday matter is made up of up, down quarks and gluons, which are inside the nucleons, inside atoms, and then outside atoms, electrons orbit. So what's all this other stuff? Well, nature decided that we have 3 generations of quarks and leptons. So quarks are up here, and leptons are down here, and there's 3 generations of them. Each generation has more mass than the previous generation, and we don't necessarily know why yet the universe is structured this way, but it is, and we tend to not see these other generations of quarks and leptons because they tend to have such high mass that they decay quickly in our detector. So we can't observe them directly in our detector. We tend to observe their decay products. Okay, so then we have the gauge bosons, which are the force mediators between the 3 fundamental forces in the standard model. The gluon is the force mediator between the strong nuclear force, which is responsible for keeping nucleons together, so the quarks together inside protons and neutrons. And the photon is the force mediator for the electromagnetic field. We interact with the electromagnetic field on a daily basis, electromagnetic radiation, radio waves, microwaves, visible light, etc. The weak nuclear force is mediated by the W+, the W-, and the Z boson. Those happen to be massive, and those particles will become more important when we search for new physics in a couple of slides. So I'll get to those in a little bit. But okay, so those are the 4 gauge bosons, and then discovered in 2012, of course, was the Higgs boson, and subsequent measurements made since 2012 have serve to kind of confirm as much as so far that this was indeed the standard model Higgs. So it fit nicely within this this kind of puzzle of what we understand to be the fundamental particles so far. And so the Higgs boson gives mass to all the fundamental particles. An interesting question would be, and one of the trivia questions actually, is the Higgs boson responsible for giving you your mass? The answer to that is no. You can blame that on the extra beer that you're drinking. Plus the extra energy inside nucleons due to the confinement of quarks and gluons inside nucleons. So it's pretty cool. The Higgs boson is only responsible for about 2% of your mass. So it's interesting. Okay, so that's the standard model. Outside the standard model, what do we know? Well, we don't have any direct evidence of anything outside the standard model yet, but that's why we're continuing to look for things outside the standard model. That's why we didn't just stop with particle physics at the end of discovering the Higgs boson. So I'll cover a few of these beyond the standard model theories and models at the very end of the talk, but there are a myriad of things that people are looking for with the Large Hadron Collider and other experiments across the world. Okay, so that's a lot of information that I threw at you. Let's kind of distill this down. What, as a particle physicist, do we find interesting? With all this information, with all of what happens in the detectors, what do we actually find interesting, and how do we sift through this data to find new physics? So let's start with proton collisions. Protons are not fundamental particles. They're made up of quarks and gluons, specifically an up quark, another up quark, and a down quark. And what tends to happen when you collide protons in the accelerator is a lot of quarks and gluons and their subsequent decay products come out. And in terms of searching for new physics, this is not that interesting in terms of we tend to see a huge spray of particles a lot, and that is not that interesting in terms of searching for new physics. So the question then becomes, how do we pick out the events that are interesting, that we want to save, and that we want to eventually compare to background to be able to see a signal-to-noise ratio, you know, a pretty high signal-to-noise ratio above our background to be able to confirm a discovery. So what mostly happens when you collide protons is something like this. This is a event display from Atlas that has a ton of what we call jets coming out of it, and jets are basically algorithmically determined sprays of particles that come from the interaction point. So each of these are would probably be characterized as a jet. This is probably a muon. And you know, there's just a whole mess of particles. So that wedge that I showed you, that comes out of the wedge that I showed you a few slides ago was not, you know, not at all reminiscent of what we normally see in the detector. What we'd like to see in terms of interesting events is something like this. This is actually a Higgs boson candidate used in 2012 to show what a interesting decay from a potential Higgs boson would look like. So these red lines here are muons. So this is this is an event where the Higgs probably decayed to 2 Z bosons, which each then decayed to 2 muons in turn. So that's an interesting event. You'll notice it's significantly less messy. So in general, hand-wavy argument here, but in general, we like to search for these types of events. Do you have a question?
Yeah. Quarks ever detected directly, or do you just infer their existence?
Right. So the question was, are quarks ever detected directly, or do you just infer their existence? So the majority of the quarks that get created are unstable particles. And actually, the short answer to your question is quarks themselves we don't detect directly. They tend to not like to exist by themselves. They are, due to laws of QCD, quantum chromodynamics, which govern quarks and gluon behavior, they tend to not exist by themselves as stable particles. They will either form into like a meson or decay into other particles. So, good question. Okay, so so this is what kind of constitutes an interesting event rather than that mess that I showed you earlier. So let's turn now to the Higgs. When the Higgs was discovered, we actually used the decay mode that happens least often. So 0.2% of the time, actually, when a Higgs boson is produced in a proton-proton collision, 0.2% of the time, 2 photons or Z plus a photon is created. And you might ask, why didn't we use the primary decay mode, bottom to anti-bottom quark pair? Well, it's because quarks happen a lot. There are a lot of processes from these proton-proton collisions that produce quarks, and it's a question of trying to get your signal, trying to get gather enough events that your signal above your background produces something reasonable. So we used the 2 photon decay mode, and then since the discovery, we've started to look at some of these other decay modes simply because we've been able to gather more data. Okay, so aside from the Higgs, the Z bosons and W bosons also decay to quarks, but also to leptons and neutrinos. So the overarching story here is that in a general sense, searching for new physics, we tend to look at these decay patterns that produce these rare events, these leptons and these neutrinos, rather than quarks. Now, of course, there are some analyses in each of these experiments that look at these quark decay modes for maybe precision measurements of things that we already know, and that's super helpful, but I'll just say that this is in the general sense. Okay, so let me distill down this information into 4 steps that will kind of help us go from proton-proton collisions in our experiment to being able to discover new particles. So step number 1, after proton-proton collision and all the particles deposit all of their energy in tracks inside the detector, we need to account for all of that and reconstruct each of those particles back to the interaction point. This takes some time, and sometimes, some cases like that event that I showed with a bunch of jets, that's sometimes hard to do because of the sheer number of particles that's happening. Also, we're colliding protons something like 600 million times per second. It's a lot of data to sift through. But assuming we do that, and we can reconstruct them back to the interaction point, we can compare these reconstructed events to well-understood processes from our standard model. So again, we're looking for new physics, and so the standard model processes that we already know and love and can simulate pretty well and understand pretty well, that's our background. And then any new physics that we're looking for would be our signal. If, after this comparison, we observe more events of a particular type than expected, we can infer that a new process is going on. But if it happens just once, well, we can't really say much. So we need to gather enough data such that this excess of this new process, maybe, is large enough that we can say with 99.9999% certainty that it's not a statistical fluctuation. We have a discovery. And I didn't just type on my keyboard whatever number of 9s that I wanted to do. So for those statistical geeks out there, that is the 5 sigma threshold. Now, not every field of science has the same threshold for discovering something new, but particle physics has the threshold of 5 sigma for being able to discover this is something new, this is not a statistical fluctuation. If it were, it would be like odds of 1 in 3.5 million chances of it being a statistical fluctuation. So this is the threshold that we use. Okay, so I'm going to show a short video here of the Higgs to gamma-gamma data collection over a 2-year period to be able to determine that the Higgs was discovered. So this is a graph showing basically the number of events on the y-axis, the zeta minus fit here, and essentially the mass of the 2-photon system on the x-axis. And you can start to see there's this bump that starts getting created, and this video will loop. So this was the decay mode, the Higgs to gamma-gamma, 2 photons in the final state, that was used to determine the existence of the Higgs boson. And an event like this happened only once out of every 100 billion proton-proton collisions. So again, we're using very not regular processes to look for these things. So 2 years of data collection was required in order to reach this 5 sigma threshold required for discovery. And then, of course, since then, like I've mentioned, we've been able to look at some of the other decay modes and also look at some of the other properties of the Higgs boson. But now that we know that it exists. Woo-hoo! So on July 4th, 2012, we found it. So that was super exciting. I was actually at Brookhaven. Like I said, I wasn't actually on the analysis team that discovered it, but I was at Brookhaven. There was a cake. There was a webcast, and we were able to watch what was happening at CERN. It was pretty cool. So now you might ask, now what? So I'll spend the next couple of minutes just kind of briefly explaining some of the beyond the standard model theories that could potentially be out there for us to find. So one example that a lot of physicists, theorists, and experimentalists alike are enthralled by is called supersymmetry. And if you've seen the Particle Fever movie at all, they kind of have this dichotomy between the supersymmetry and the multiverse. It's a little more complicated than that, but it is a really elegant theory, and it's a really interesting one, and a lot of people are putting a lot of work into it. And the basic premise, I'm not an expert on it, but the basic premise of supersymmetry is that each of the standard model particles have a supersymmetric partner particle. So each fermion in the standard model would have a supersymmetric boson partner, and each boson in the standard model would have a supersymmetric fermion partner. And there's all sorts of theorists, working out the math on that. And there's a lot of theories that have this property that we're trying to look for with LHC data. Another interesting beyond the standard model outlying question, is what is dark matter? And that is something that a lot of theorists have said that, the LHC can potentially produce dark matter candidates. So a lot of people are looking at different types of dark matter candidates. One you might have heard of in some of these astronomy space talks is the weakly interacting massive particles. That potentially could be produced at the LHC, who knows? So a lot of people are looking at different dark matter candidates in order to search for what the nature of dark matter is. A theory that is, or a series of theories that's kind of near and dear to my heart, which is what I work on, is a model that is non-supersymmetric. So it's not related to supersymmetry, but it kind of provides an alternate way of answering the questions that supersymmetry answers. And in particular, a lot of these theories require the existence of heavier quarks. So maybe fourth generation quarks, maybe just other quarks of particular types. And so this is essentially just showing a couple of those particular quarks, heavier quarks, that could potentially decay to the standard model top, which is the heaviest particle in the standard model, and or the standard model bottom, and could potentially decay to Higgs or Z or W bosons. And then, of course, all of those particles we don't detect directly, we detect their decay products, so then they decay into the observables that we detect in the actual detector, and so we're essentially looking for excesses of the number of events of these observables. And if you're interested in these plushies, particlezoo.net actually has a whole series of plushies that represent each particle in the standard model, and they're antiparticles. So those are kind of cute. Okay, so I'll just end there with kind of some bullet points on the future of the Large Hadron Collider. So currently we're operating at 13 TeV, so that's tera electron volts. That is a unit of measure that we use. It's pretty small. If you actually like converted it to joules, it would be like the amount of energy that a mosquito, flaps its wings at. But on the scale of a proton, that's huge, and it can potentially produce very heavy particles that are much heavier than the proton themselves. So that's why we need high energies. So we're currently operating at 13 TeV. We hope to go to 14 TeV soon. We're operating at design intensity, which essentially means how many collisions per second. In 2018, we're going to be shutting down all of the facilities for maintenance and upgrades to the various detectors. The U of A is actually involved heavily in part of the Atlas upgrade, and actually in the first prior to the first run of the LHC, the U of A was actually directly involved in building a huge part of one of the forward calorimeters for Atlas. And currently we're involved with the electronics for some of the muon spectrometer upgrade. Then a few years after that, we hope to be operating at peak energy and 2 times the design intensity. And of course, anytime between now and then, stay tuned for discoveries of new physics, because that should be pretty interesting, and we're definitely hoping to find something. So thank you. I will take your questions now.
Okay, we can take some brief questions for Sarah as we transition speakers.
Yeah.
How much mathematical humanity is what's going on, sir? Is it the doubt at all?
I would say not much doubt at all. Again, we're colliding energies, that are important on the proton scale, but it's not anything we need to be concerned about. Actually, yeah, okay, go ahead.
Have to phase these protons phenomenally well to get them to collide at the right place.
Right, yeah. So those in that video that I showed you on like the second slide, so the question was, you might have to make sure that these proton beams come into collision at exactly the right spot. And yes, there is fine tuning in the magnets that goes on, and yes, precision is key. And there's like a small cross section of the interaction of like something like a centimeter where the protons actually do collide. But yeah, it's a huge deal, and a lot of technicians and engineers work heavily on that.
They're nearly at the speed of light.
Yeah, exactly. They're nearly at the speed of light. So yeah, it's important to get them right on beam. But it's also, so like I mentioned, these are proton bunches. So each bunch has approximately 10 to the 11 protons in them. So it's a bunch of, this is a macro scale, but like it's a bunch of protons, and even out of 10 to the 11 protons in each bunch coming into collision, you're only going to get, something on average of like 10 collisions of actual proton-proton collisions. Single proton, it's more like, it's on that scale, it's more the gluons inside the protons and the quarks inside the protons are actually coming into collision. But yeah, it's precision physics. So, did you have a question?
How long before a bigger collider is actually built?
So there are a couple of larger colliders that are in the works, and I think there might be one in China or some other Eastern country that is looking to build a bigger one. But I think the last I heard was that there are a few proposals to build larger colliders at higher energies, and some of them are looking at linear colliders, and some of them are looking at larger colliders. There's one that is looking at using the LHC right now as one of those synchrotron boosters to boost particles even higher into a larger LHC style, larger ring that's like 100 kilometers in circumference. But I'm not sure if that's gonna go through. That was just in the like proposal stages right now. So, but I don't know what the next biggest one is gonna be, because I don't know if they've gotten approval to build it yet.
There's nothing getting funding, direct funding.
There might be, but yeah, I don't know.
We'll probably be able to have time afterwards to be able to have questions more after both speakers are done. So transitioning to our next speaker, we're going to have Dave O'Brien talk about Dawn's exploration of the dwarf planet Ceres. He's a participating scientist on the Dawn mission, and he even has an asteroid named after him.
Well, it's a really high number, though. It's not that good. all the good ones were taken by the time I got into the field. Okay, well, thank you everybody for coming out tonight. I'm going to jump right in and kind of give a little bit of background on the Dawn mission before I start talking about some of the recent results. So the Dawn mission is it's an interesting mission. It's a first for NASA missions and any kind of planetary mission, in that it's going into orbit around two different bodies. So it was launched in 2007. Did a Mars gravity assist. Can everybody hear me? Am I holding the mic close enough?
Louder.
Louder. Okay. Oh, there we go. Got it. So it did a Mars gravity assist. Basically, got a little extra slingshot from Mars into the asteroid belt. Went into orbit around Vesta, the second largest asteroid in the asteroid belt, for about a year. Left orbit, and then last year it got into orbit around Ceres, which is the largest asteroid in the asteroid belt. Ceres is actually classified as a dwarf planet, which is kind of an interesting distinction. It's more terminology, but it basically means that it's big enough to be more or less round, whereas all the other asteroids are lumpy. I'll show a little bit more about that in a minute. So basically at each target, Dawn has various instruments. It images the surface, makes a topographic map, so the elevations, digital terrain model, maps the elemental composition, mineralogical composition, measures the gravity field, and searches for moons. So the way it does that, it has these three instruments. There's the framing camera, which is kind of basically a digital camera. It has different color filters, so it can take broadband images in different wavelengths, and then just a clear filter, so it's kind of like a monochrome grayscale image. I'm going to talk mostly about that, since that's what I'm most familiar with, and that's what has most of the best data so far. There's another instrument called the Visual and Infrared Mapping Spectrometer, or VIR. That goes out to 5-micron wavelengths, so into the infrared. That's good for determining the mineralogical composition, so telling you, do you have olivine, pyroxene, things like that, silica, picking out different spectral features that can tell you what kind of minerals the surface is made out of. And then there's a grand instrument, which looks at gamma rays and neutrons coming off the surface and can tell you more about elemental composition, so how much hydrogen, how much iron, how much silicon, things like that. So these three altogether are basically looking at the surface more or less continuously, integrating data and basically building up a big database about what's going on and what it's made out of. In addition, since the spacecraft is in orbit in the gravity field of these bodies, if the gravity field is a little irregular, it gives little nudges. And we can track the little tugs on the spacecraft and figure out what the shape of the gravity field is, essentially. And that can tell us what the interior structure is. So that's very important to know as well for determining what the evolution of these asteroids has been. For both Vesta and Ceres, there's several different orbital phases. So it gets into orbit. Here's the Ceres in the center. It gets into orbit fairly far out, and then moves through these successively lower orbits. So the RC3 phase for rotational characterization, then survey HAMO for high altitude mapping orbit, and then LAMO for low altitude mapping orbit. So we're currently in the LAMO phase right now. That's giving us 35 meter per pixel resolution images, which is pretty high resolution. So it's not quite as good as some of the moon missions and the really high power Mars missions that we have now. But you can pick out things that are like, sort of on the scale of this building. which is almost unprecedented resolution for full surface coverage of asteroidal bodies. So a little bit about background about Ceres and the discovery of Ceres. It was discovered in 1801 in Palermo, Italy, by a Catholic priest astronomer named Giuseppe Piazzi. It's named after the Roman goddess of agriculture. It was the first asteroid discovered. So sometimes you'll see asteroids. So I said my asteroid number is like 22,000 or something like that. Ceres' asteroid number is 1 because it was the first discovered, and that's kind of how they place them in how they number them. It's the largest asteroid. It's about just under 1,000 kilometers in diameter, about 600 miles. It's about twice the size of Vesta, Vesta being the second largest asteroid and the first target of the Dawn mission. The surface gravity is about 3% of what we have on the Earth, and the escape velocity is about 500 meters per second. So on very small asteroids, if you were standing on the surface and you sneezed, you'd be gone. Ceres, you could do some really awesome long jumps, slam dunks, things like that, but you wouldn't really be able to leave the surface. So it's a lot lower gravity than the Earth, but there's still enough that you'd be in a bound orbit if you jumped. You'd come back and just might take a look at it. It'd probably be pretty fun. So a little bit about the discovery. I should note the little figure on the bottom just kind of shows the a schematic map of the solar system. There's the terrestrial planets, Mercury through Mars, the asteroid belt, where Ceres is located, then Jupiter, Saturn, Uranus, and Neptune, and then the Kuiper belt and trans-Neptunian bodies beyond there. So this asteroid belt zone is kind of interesting. People have predicted for hundreds of years that there really ought to be a planet there. They knew about all the other planets, they knew about Mars, they knew about Jupiter. Not long before Ceres was discovered, Neptune was discovered. So they were like, okay, we know something's there, we just got to look really hard for it. So there was actually a big international collaboration to basically scan the sky down to really faint magnitudes and try to find that missing planet that's hanging out in the asteroid belt. There was something like 20 people involved in this. Piazzi's role is kind of interesting because he was originally on the list, but as far as I can tell, never got the invite. Like, he kind of got told about it after Ceres was discovered. So this group formed, he was supposed to be there, but they never told him anything about it, and they were doing their thing. And so he was doing his thing at the university, at the Palermo Observatory. Using this, here's the Palermo Observatory building, the little dome on the top. This is the instrument that he was using. It's not a very powerful telescope, but it was set up to make very high precision measurements of the positions of stars in the sky. So that was what his job was basically. He was looking at 7,000 different stars or something like that over the course of a year, measuring their exact positions and seeing if there was any little shift during different parts of the Earth's orbit, which can actually tell you how far away those stars are. But one night, back in 1801, he was following up on one star that he saw the night before, and it wasn't there. Wow, okay, that's kind of weird. Maybe I'll just nudge around and see, oh, there it is, it's just a little off. And then the night after that, same thing, it was a little off in that position. So the stars are mostly fixed for all intents and purposes in the sky. So if you see something moving across relative to the stars, that's generally something in the solar system. So the planets do that, comets, asteroids, things like that. So he was like, wow, this is pretty cool. So let me talk to my friends, the mathematicians. We'll work on this. We'll try to figure out the orbit. And they figured out, okay, yeah, this is a body in the asteroid belt. So initially, some people thought it might be a planet. And of course, there's definitional things here. But it became clear pretty quickly that it wasn't all that big. It wasn't as big as Mars or anything like that. And also within a few years, I think within 3 or 4 years, there were 4 or 5 more large asteroids discovered. And then after that, there were dozens more. So fairly quickly, it became clear that, all right, this is a population of small bodies between Mars and Jupiter, not really one big planet that's hanging out there. So even though he never got the invite, he made the discovery, and I bet everybody was a little upset about that. Not him, of course. So for a long period of time, basically since its discovery in 1801 to about the 2000s, Ceres was pretty much just a point of light. So the telescopes couldn't really resolve it. It was really just one pixel there. They could take spectra and things like that and try to determine the composition. But in 2003 and 2004, the Hubble Space Telescope was used to image Ceres. And this is a very enhanced color image of Ceres taken by the Hubble Space Telescope. But this is the one that usually shows up in the literature when you see it. And they were able to get, I think, something like 30 pixels across it. So they got a pretty good determination of what its ellipsoidal shape was. And from the shape, they could actually determine that there was a central condensation. So rather than being just a totally uniform body with everything thoroughly mixed, the denser stuff is sunk to the center and the lighter material was on the outside. This is pretty important because a lot of asteroids, the vast majority, don't seem to be differentiated. They're just primitive material that never melted and reshaped itself. The mass of Ceres, even before Dawn got there, can actually be measured by looking at other asteroids and looking at the little nudges and tugs that Ceres gravity puts on those other asteroids. So their orbits change ever so slightly, and by building up repeated observations of how this happens, what the outcomes are, you can determine the mass. So from Hubble, we had the size of Ceres, we have the mass of Ceres, and you can calculate a density, and that came out to be about 2,100 kilograms per meter cubed. So this is interesting, because if you had like rock or rock-iron mixture, which is what most asteroids are, it'd be like 3,000 or something like that. And this is like 2/3 of that. Pretty much the only thing people could think of that could give you this low density is having a significant amount of water ice in there, because water ice is a density of about 1,000 grams per meter cubed. So that was another interesting thing that came out of that. So Ceres is like maybe not like all these other rocky asteroids. There might be a significant water ice fraction. And if so, what is it doing in the asteroid belt? How did it get there if everything else is rocky? So people did some thermal models to see, well, if you had this rock ice mixture and you had a mixture of radioactive elements early in the solar system, what would happen? And one of the things I came up with is that you might actually be able to melt it, form a liquid water ocean underneath the surface that's stable for a period of time, possibly even to the present day, although I think people are kind of backing off from that now. But certainly at some point in the history of Ceres, liquid water below its surface is a distinct possibility. And certainly material would have had to melt enough to mobilize so that the dense stuff could settle to the interior and the lighter stuff could rise to the surface. So here's a few snapshots of Ceres on the approach. So this is the first multi-pixel image that Dawn sent back. It's 8 pixels across. Okay, not too impressive. Still well below Hubble. This is one of the first ones that's getting close to Hubble resolution. You can see this bright spot here. These ones are about 4 times Hubble resolution. You can start to see some actual details. It seems like there's a large impact basin here. We'll see that better in some of the next images, and more bright spots as well. So Hubble had something like 30 kilometers per pixel resolution, and they were able to tell that there were color variations, there were brightness variations, and things like that. But as Dawn got closer and closer, we were starting to really see that in detail. So here's from, let's see, from actually about a year ago, one of the first like really good images where we're really starting to see stuff. You can see these neat grooves in the South Pole, another impact basin here. The bright spot resolved into 2 spots, and it was found that it's right in the middle of a crater. So from a year or more ago, this was like the most interesting thing on Ceres. That was what everybody wondered about. What the heck is that spot? Maybe I'll answer that by the end. We'll see. So here's some of the, let's see, from the RC3 phase. So this is basically, Ceres is filling the full frame of the detector on the spacecraft. So these are kind of the last images we had where you can see Ceres as an entire body, not just a subset of it. So again, you see the double spots here. That crater that the spots are in is called Akator crater. There's these 2 large impact basins in the southern hemisphere, Uvara and Yalode, or switched, I can't remember which order they go in. There's this other on the limb here, you can see a very flattish but distinct round impact basin called Kirwan. That's the largest well-defined impact structure on Ceres. So it's kind of interesting that on Vesta, and I'll show an image of that in a minute, we have 2 impact basins in the south pole of Vesta that are like 400 and 500 kilometers in diameter. Ceres, which is like twice the diameter, about 8 times the surface area, only has 3 large impact basins, and the largest of them is only about 300 kilometers in diameter. So there's a big question like, why don't we see really massive impact basins on Ceres? Where'd they all go? And that's still kind of an open question. I think it tells us a lot about Ceres evolution, what might have happened early on, what its composition might be that allows for the relaxation or erasure of these basins. But that's a very distinct difference that we saw very early on between Vesta and Ceres. So this here is a movie from a bunch of survey images stitched together into a mosaic and put over a shape model. It should show you the whole body as it rotates. Again, here's the South Pole impact basins, Uvara and Yalode, Akator crater. We should see the Kirwan impact basin coming around here. So in general, you can see there's a lot of craters, random white spots all over the place, not just an Akator crater, but generally associated with craters, and often some like big linear features and things like that. The next one is basically the same thing, although I've put color-coded topography over, and that really helps show in a lot better detail the ups and downs of the surface. The range is something like 8 kilometers from the highest point to the lowest point. So it's relatively flat. There's not a huge amount of topography, but you can see like the red here is a fairly high region, blue is low. Here's the Kirwan impact basin again. So there is some variation over the surface, but in general, there's not like massive mountains or enormous valleys. But there are a lot of subtle topographic features. So one of the things you might note, if you've seen pictures of asteroids before, these of course are not asteroids, but this is generally astronomers use them as asteroid analogs because of their shapes. Ida was one of the first asteroids visited by spacecraft. It was actually seen by the Galileo spacecraft as it was flying by on its way to Jupiter. Lutetia was visited by the Rosetta spacecraft as it was on its way to a comet. Lutetia was, before Vesta, the largest asteroid visited at about 100-kilometer diameter. And you can see it still has that more or less potato shape. Ida is more of a peanut. But definitely not round and smooth. Even the second largest asteroid, Vesta, which of course was the first target of the Dawn mission, it's more round, or more kind of like a ellipsoidal kind of shape. But there's still some fairly sharp topography on it. You can see these big impact basins, or impact craters here, the snowman trio of craters. And in the South Pole, there's this large impact basin named Rhea Silvia. You can see the big rim scarp there, the central peak. So it's closer to an ellipsoidal shape, but it still has very rugged topography compared to Ceres. So why is that? Well, let's look at one thing. It basically just has to do with size. That's one of the important factors. So all these little things that you probably can't see up until about Lutetia are other asteroids that were visited by spacecraft, and this is all to scale. So there's Lutetia at about 100 kilometers diameter, Vesta at about 500, and then Ceres at nearly 1,000 kilometers diameter. So Ceres is definitely the biggest one by far. And the bigger something is, the stronger its gravity is, and the more effective it is at squeezing itself into a more or less equilibrium spherical or ellipsoidal shape. So even though it's big amongst asteroids, we can compare it to other bodies in the solar system. So here's Vesta, here's Ceres, here's the Moon, Mercury, and Mars. So it's still pretty small by Planetary, in comparison to our Moon and other planets. And so Vesta, if you were to take a map of Arizona and put it over Vesta, Vesta's diameter is about the width of Arizona for scale. And the Moon is like kind of, if you put it over the United States, it would kind of fit. Just to give some non-astronomical context. And finally, to compare to some other icy bodies, here's Pluto, which has recently been, there was a flyby by the New Horizons spacecraft, which returned some very amazing data. That's about twice the size, more than twice the size of Ceres. Dione and Enceladus are two icy satellites of Saturn. Ceres is sort of, comparable in scale to those icy bodies, those in the outer solar system around Saturn. Okay, so I said one of the things has to do with size. The bigger something is, the stronger the gravity is, and the easier it is to squeeze it into a more or less spherical shape. But composition has a lot to do with it too. So I noted before that Ceres probably, just given its density, has an ice-rich composition. As we started to look at the surface in more and more detail, we are seeing more and more signs of like, yeah, there is more ice here than other asteroids we've seen. So it's the surface is not pure rock. So one of the first things we noticed was a lot of the craters, these little scale bars here are about 5 kilometers. So these are 20, 25 kilometer diameter craters. A lot of them on Ceres tend to be fairly shallow, and many of them have central peaks. So you can see some prominent central peaks here. This is consistent with an ice-rich composition for Ceres. The reason central peaks are a good indicator is that icy bodies tend to be weaker. So when a crater forms, if it's in a rocky body on something with a gravity comparable to Ceres or Vesta, you need to get a really, really large impact before it really rebounds and gives you a central peak. So on Vesta, the only central peak crater is really the big South Pole impact basin, 500 kilometer diameter Rhea Silvia. Once you get to On Ceres, however, we see central peak craters down in the 20-kilometer range. Basically, the ice-rich surface makes it weak enough that for a relatively small crater, you can get that rebound that forms a central peak. If you've ever seen like a slow-motion video of a drop of milk falling into a flat surface of milk, you get that kind of crown thing that's forming. That's more or less the same thing that's happening. In a high-speed impact, you basically fluidize the material and get that kind of behavior. So it doesn't really behave like a solid anymore. But the icier it is, the weaker it is, and the more fluid it's going to be, so the more likely you get these central peak craters at small sizes. We can set an upper limit, though, too, to the ice fraction. If it was 100% ice, given the surface temperatures that you'd have in the asteroid belt, everything would just relax away. It would be basically gooey and runny enough that everything would smooth out like a cue ball. So we can say that Ceres has a surface that is consistent with something like 50% ice fraction, or maybe a little bit less than that. If it had much more than 50% ice, we wouldn't really see any craters to begin with. We also see a lot of these interesting flow-like features on Ceres as well. Most of them are associated with impact craters that seem to destabilize something. So in the upper corner here, there's one. You can see a kind of tongue-like flow coming out. Here's another one on the wall of a crater flowing out. We see these all over the place on Ceres, but they're more common in the northern regions, which is maybe where you would expect to see more ice near the surface because it's colder there. The morphology, kind of the shape of these, if we look in detail, they're a lot more similar to terrestrial craters than dry landslides. So if you kind of look at the topographic profile, what their shape is, they look, I think they're called rock glaciers on Earth, basically, where you have an ice-rock mixture that flows almost like a fluid over very long time scales. It looks more like that than if you just take a bunch of granular material and let it slide down a hill. So that's yet another indication that there may be ice-rich material fairly close to the surface. And this is not something that we see on Vesta or any other asteroids as well, any other rocky bodies. So it seems to be fairly unique to Ceres. Another thing that we see, again associated with craters, since most of the surface of Ceres is dominated by craters, is that there's a lot of smooth regions, often inside of craters, like this one here, and sometimes exterior to craters as well. This is generally interpreted on other bodies and on Ceres as well as being the result of impact melt. So this is kind of interesting, because in the asteroid belt, the impact velocities are generally too low to give you significant amounts of melt for a rocky target. On something like the moon, on the Earth, where the impact velocity is a lot higher, you can melt rock, but not so much in the asteroid belt. However, ice is a lot easier to melt in impacts, and especially if you have something like some salts mixed in or something like that, maybe ammonia that lowers the freezing point, it's actually fairly easy to melt ice in impacts. So this is yet another sign that there's something about the surface of Ceres, most likely an ice-rich composition, that's giving us this interesting morphology compared to the other rocky asteroids. We see a lot of these interesting linear features all over Ceres, but one particular class occurs on the floor of large craters, generally smooth floors where there's a lot of suspected impact melt. So this little ridge set is kind of interesting. This looks like a chain of craters, but it's actually a crack where the little individual crater-shaped things are where material drains down into the crack. This is in the floor of the Yelloide crater, which is one of the big South Pole impact basins. This is another crater called Gantu. Again, it has a very smooth floor. You'll see a few white spots here and some little cracks. This was a HAMO image, and we recently got some low-altitude, high-resolution images of that area in detail. And it's quite complex. It's not like there's just one little crack there or something like that. There's this very interesting kind of network of cracks in the impact melt sheet of this crater. When I first saw this, and other people as well, it reminded us of a lot of craters that you see on the moon. So this is Humboldt crater. I think this is maybe an image from the Apollo 15 module flying over. But you can see a flat floor, lots of cracks here as well. These dark regions are actually pyroclastic deposits, so like a lava fire fountain kind of thing as well. Not sure if we quite have that on Ceres yet, but there may be some sorts of volcanism as well. I'll get to that in a minute. But the cracking seems very similar. So this could happen on the moon. It's interpreted to happen when lava intrudes under the floor of a crater and actually lifts it up and causes cracking. You could also get it forming as well just from the solidification of a melt sheet and pressurization of material below the melt sheet that's still freezing out and things like that. The exact details are a little uncertain, but it's something that we see in a lot of craters and seems to be an important tectonic process within the craters. We also see a lot of cracks outside of craters as well. And it almost seems like any point on the surface you look, if you look in enough detail, you start to see these linear features. So they sometimes look like well-defined cracks. Sometimes they form these little pit chain things. Like I noted before, if you have a crack and then fine granular material over it, that material drains into the crack and gives you this appearance of a linear chain of craters. And you can see these here all have a preferred orientation. This one as well. So go back for a second there. So this is generally interpreted to be surface expressions of cracks, possibly deep cracks in the crust. Possible tectonic features. So something happened to move or deform or crack the crust to give this surface expression. My preferred idea for this one, and something we're still working on. So how many of you have, you want to get your beer or your soda really cold, so you put it in the freezer, and then you have another beer while you're waiting, and then you forget about it, and the next morning you find that like it's blown out, right? So if Ceres had an ocean, a subsurface ocean that was freezing out, that's going to expand as it turns to ice and actually stretch the shell, and could be one possible source of these large-scale cracks over the entire surface. Some of the cracks as well are associated fairly locally with craters, so it could just be fractures from the impacts. But it does look like there might be some sort of global scale thing going on as well as a result of Ceres evolution. Another way we see another manifestation of these cracks is that a lot of craters on Ceres seem to be polygonal, mostly hexagonal, but sometimes like square or other shapes. This one you can see almost every crater here seems to be non-circular. This is generally interpreted to be the result of having a pre-fractured surface, and when you form a crater, the crater collapses and the orientation of the fractures gives you kind of a preferred orientation of the walls of the crater. If anybody's been to meteor crater or seen like an aerial image of meteor crater is not round. And people have actually done a lot of work mapping the faults and joints, which is basically a fault that's not really, or a crack that's not sheared. But mapping those throughout the entire region around meteor crater, and they basically found that the walls of the crater are oriented as you would expect based on the pattern of cracks. So it seems like even if we don't see a surface expression of a crack, like the actual crack or a pit chain, a lot of these craters might be telling us about a pre-existing tectonic fabric. And then sometimes too, we see a pretty good example where at least my eye kind of picks out a sort of a linear feature here, almost like kind of a little ridge that coincides with the wall of one of the craters. So, so that's a case where you can actually see the kind of the crack coinciding with the polygonal crater. Okay, so now on to everybody's favorite crater, or at least the crater that's inspired the most curiosity. This is, again, is Akator crater. It's about 90 kilometers in diameter, and it's the best case we have for, or the best example we have of these bright spots. And so from a distance and from the ground, we knew that there was one spot. It resolved into two, and then one of the spots resolved into all these other little spots. And it's kind of hard to see here, but if you look in detail, or at least on the screen, you can see that there's some cracks associated with them as well, with both sets of spots. There's very few superposed craters on this crater, so that basically means it's young, and the edges, the rim of the crater is fairly sharp. So over time, Ceres gets hit with more and more impacts, and that erodes things away. It puts more craters on top of old craters. So the more craters you see on something, the older it is. And this has almost no craters on it. So it could be, you know, maybe not yesterday, but on the order of like tens or 100 million years, which in solar system terms is fairly young. So we don't really see very old craters, very eroded craters that have these white spots as well. It seems to be something that we really see with just the youngest craters. And Akator crater seems to be one of the youngest, if not the youngest, big craters, and it also, maybe not surprisingly, has the best developed white spots, or the white spots have not faded yet, is maybe a better way to put it. So this is a movie of Akator, just showing it from different orientations. So you can see it's not, it's a few kilometers deep. It's fairly relaxed with a fairly flat floor. There's a little bit of a central peak. It almost seems like the white spots, at least in the center, are in a little bit of a dip there. And then I'll show the topographic image where it's shaded by height next. So you can see that the white spots generally occur in the lowest points within the crater. The dark blue is the lowest area. So there's a lot of speculation as to what these could be. A lot of possible analogs that people are looking at. So a few of them, and we have this one's kind of interesting because the Mars Geoplasmin, what's your spacecraft called?
Mars Reconnaissance Orbiter.
Okay, sorry about that. The high-rise camera on the Mars Reconnaissance Orbiter has re-imaged the surface of Mars in various spots over and over. And they can actually get repeat observations and sometimes find new craters that have formed less than a year ago. And then when they find a new crater, they can do follow-up observations and see how that crater evolves. So this one, this is probably on the order of tens of meters. The Mars Reconnaissance Orbiter has a very high-resolution camera. This white material is exposed ground ice. And this is looking at it just a few months later, and you can see a lot of that ice has gone away. Basically, at the temperatures of the surface of Mars, it's not going to melt, but it's going to sublimate. So basically, like the ice cubes in your freezer eventually go away even if you don't do anything, do anything about them. It basically goes straight to vapor. So on Mars, that happens fairly quickly. So that's one possibility. Maybe the spots of Akator, if that crater formed very recently, it could be exposed ice. The problem there is that ice goes away so fast, even in the asteroid belt where it's a little further out and cooler, it goes away so fast that we'd have to be really lucky to have, the crater probably would have formed within, decades or like 100 or a few hundred years, which is statistically really, really unlikely for a crater that size. It's also been speculated that, well, maybe if there's a subsurface ocean, it's still active today, you could have geysers or something like that, something actually spouting liquid water out onto the surface. So you could see maybe ice deposits from that, or you could see salty, like brine, evaporite deposits that were left over from the water. It's certainly a possibility, but that's sort of one of the most dramatic things. A more likely case is impact-driven hydrothermal activity. So Ceres has ice in its surface. Impacts generate heat and can melt some of that ice and form liquid water and deposit heat in the rest of the material as well, and cause this very fractured structure within the crater. So on Earth, we can actually go and look at impact craters, dig into them, figure out what was going on, and all of them seem to have some sorts of hydrothermal systems. So on Earth, that happens because there's groundwater, and groundwater mixes with the hot rock. On Ceres, it'll be a little different because you're melting material, and then that's being kept warm by the impacted surface. But the basic idea is the same. You could generate liquid water, mobilize it, and maybe dissolve some salts and redeposit them on the surface. So this isn't quite as dramatic as a geyser blowing material out onto the surface, but it's something that could mobilize water, mobilize salts, and possibly lead to some salt deposits on the surface. And analysis of the composition of this material, we can't definitively say, but it seems fairly consistent with like carbonates and salty deposits and things like that. All right, I think I'm going to get trained in about 5 seconds. So everybody raise your glass. Go to the routine. Choo-choo. Okay, well, I'll keep talking until it gets too loud. So one of the interesting things, a little bit before the arrival of the Dawn spacecraft, the Herschel Space Observatory was doing observations of Ceres, and okay, no, we'll stop. Hold that thought. Okay. So the Herschel Space Observatory, which is observes out into the infrared, and I believe the far infrared, maybe into the microwave range as well, was doing observations of Ceres as it rotated. And what it found was that for particular longitudes, there was detectable water vapor absorption. So not for the entire body, so it's not like there was a whole cloud there, but particular orientations of Ceres, there was a strong water vapor absorption. So there were two spots where they found this. And what's interesting is that those two spots with the strong water vapor absorption, one of them corresponds to Akator crater. The other one corresponds to this region kind of north around the Kirwan impact structure that's generally bright, but it's not really a point source. So this is consistent with if you had 6 kilograms per second of water vapor being put out, which is not really all that much. That's consistent with what the Herschel Space Observatory detected. So you don't have to have these massive sheets of ice that are subliming away. In fact, if you just had about 1 kilometer square of ice, which is a fairly small amount, much smaller than the size of the bright spots in Akator, then that would be enough to give you the amount of water vapor that was detected. So it doesn't, when this discovery was, how the press release images showed these like artist conceptions of these geysers like blowing material off of Ceres, like that's not necessary. It would be a very subtle effect. So that could still be consistent with sort of a long-lived, like the waning stages of a hydrothermal system, still putting a little bit of water vapor or a little bit of exposed ice sublimating away within Akator crater. But it's still kind of a mystery exactly what's going on there. So I'll leave Akator at that for the moment. I will note, as you probably saw from the movie before, that there's a lot of other bright spots. Almost all of them are associated with craters. This one here is called Oxo crater. It's kind of interesting because there's one side of it actually kind of collapsed inwards. And I'm not sure if this is published yet, but people have done some spectroscopic measurements and seem fairly confident that they're actually detecting exposed ice there. Not even just inferring it, but actually detecting the spectral signature of exposed ice, which is maybe something you could expect if this landslide event happened fairly recently. Some other craters as well. Sometimes you'll just see little spots like in the floor of Dantu. Other times, I think this is Halani crater, almost the entire thing and some material thrown out from it is fairly white. And as I noted before, this is generally something we just see with fairly young, fresh craters, not old ones. Basically, over time, whatever that white material is just gets kind of mixed into the surface by subsequent impacts. Okay, so one final kind of interesting feature that I'll focus on for a little bit. It was called the pyramid, which unfortunately led to all kinds of wonderful conspiracy theories. So just go to YouTube, type in pyramid on Ceres, and yeah, you'll find some really awesome stuff. But the actual real stuff, I think, is also still kind of awesome, if somewhat puzzling. So in some of the far out images, we could see, it rises fairly prominently above the surface, and it's fairly bright as well. It's sort of like, wow, what's that doing there, and why aren't there any others? As we got to higher resolution, we got some better images of it, and it's kind of interesting. It's not just like a rounded dome or something like that. You can see that it's very, it has a flat top, these very steep sides that are basically at the angle of repose, so about as steep as you could pile material up. And it meets very sharply with the surrounding floor, so it's not like there's a smooth run out where it blends into the surface. Here's an image frame showing it, and here's just a topographic frame to show. It's the highest thing right around there, but there's also some other interesting topography around as well. There's some other lumps and things like that in the region, but this is certainly, Ahuna Mons is definitely the most well-defined feature like this in the area and over the entire surface. Here's another movie showing basically all orientations of it. You can see most sides are fairly sharp, although I think that's the south-facing side is fairly gentle, almost like the pre-existing surface kind of got tilted up a little bit. But all other three sides are fairly sharp and steep. The material on the top, it looked like it could just be maybe the cratered pre-existing surface that got lifted up. When we look in really high resolution in some of the latest images, it doesn't really look like the pre-existing surface. It looks much more cracked, not just kind of like a cratered surface that got lifted up. So it's not clear exactly what's going on there. Again, here's a topographic image. So the white is the highest and grades down to blue is the lowest. People have speculated that this is a possible cryovolcanic feature. So basically, if you have cryovolcanism is basically volcanism with ice and water instead of rock and magma. Another possibility is that there was sort of a low-density material below the crust that actually moved up and lifted up some of the pre-existing surface. It's still kind of unclear of all the competing theories which one best explains the observations. I'm not really convinced of anything yet. Although it is kind of interesting that we really only see one feature like that. If you see 0 or like 1,000, then it's pretty easy to come up with an explanation for like that, but for things like that. But if you only see one thing, it's really hard to say, well, here's this very specific set of circumstances that cause this one thing to form here but nowhere else. But as we look in more detail over the surface, I think I kind of noted before that Ceres might be kind of smooth it's not really jagged, but it's still kind of lumpy. This is sort of a 50-kilometer scale dome type feature. There's another one here that's even smaller in the high resolution images. And this one almost has some steeper looking sides, kind of like a Hunamans, but not quite as good. So it's possible that there's basically a continuum of features like this: young ones, well-developed ones, old ones, and a Hunamans is maybe just the one that we're capturing at its peak. So when it's just formed, when everything is really fresh and it hasn't had a chance to get eroded down by subsequent impacts. But it's still quite a mystery exactly what was going on to form it. Okay, so my final comment here. I've talked a lot about how there's a lot of evidence for an ice-rich composition of Ceres. Mainly from geomorphological evidence, so just kind of looking at the features on the surface, comparing them to rocky things and ice-rich things. A lot of the features seem to be more consistent with ice-rich material than rocky material. There was also spectral evidence for materials called ammoniated clays. So basically, clay-type soils, but with ammonia and ammonia-type compounds embedded in them. This was very interesting because in general, people don't think that this would have been able to form in the asteroid belt. They think that this type of chemistry is a signature of things that come from the outer solar system rather than kind of the region between Mars and Jupiter. So there's competing ideas that, okay, maybe there's ways you could form these within the interior of Ceres. But it's still another piece of evidence suggesting that, well, maybe Ceres is an interloper in the asteroid belt. That's not really as crazy as it might sound. So a lot of the up until maybe only about 15 or 20 years ago, the basic idea was that the solar system formed fairly calmly. Everything formed more or less where it is now, and it was just totally fine, stayed right there for the next 4.5 billion years. Over the last 15 or 20 years, it's become increasingly clear that there's been a lot of dynamics in the solar system, scattering things around, moving things around, both the giant planets, maybe even some of the terrestrial planets getting knocked around from their initial locations. So the asteroid belt is, some people kind of call it the dumping ground of the solar system, because it looks like a lot of material, both from the terrestrial planet region and from the outer solar system, can get knocked into there during various stages of planet formation. This movie here, I'll show it in a second. The 4 rings here are Jupiter, Saturn, Uranus, and Neptune. The terrestrial planets in the asteroid belt are all in the center of that. And here's sort of a proto-Kuiper belt. There's a model called the Nice model, because all of the scientists were working in Nice at the time, that postulated that the giant planets would migrate due to interactions with this planetesimal disk, slowly move outwards, and eventually their orbits would cross a mutual resonance that would destabilize the system temporarily, scatter lots of material around. On the right, it's basically showing a plot of the known asteroids, and then I think the red dots are all bodies that were originally out here that could be captured into the asteroid belt. And the zone where Ceres is sort of the innermost edge of where you could potentially put some of that material from the region beyond the giant planets. So we can't really say conclusively that Ceres is an interloper, but it's certainly plausible and would fit with a lot of the sort of weirdness. It seems to be kind of a very large ice-rich body in an otherwise mostly rocky region of the solar system. So thank you for your attention, and I'll take any questions.
So we know we have meteorites in our collections from Vesta. What are the prospects of getting meteorites from Ceres, and if so, what would they look like?
Yeah, that's a really good question. So Vesta, in addition to being the second largest asteroid, it was also very interesting because we had very good evidence that we have rocks on the Earth that came from Vesta. There's sort of a chain of evidence that I think is very, very strong linking those meteorites to Vesta. So we could actually, people have been studying those rocks for a while, and then we could actually go and look at the body they came from, rather than kind of the opposite, where you study the body for a while and eventually go and get samples. Ceres is a fairly primitive body, so the spectrum is more or less flat. There's not a lot of well-defined features. It's fairly similar to a lot of meteorites called carbonaceous chondrites. So Vesta meteorites are called the Howardites, eucrites, and diogenites for the different classes. But there's not a particular class of meteorites where we can say, yeah, this one really looks like it's Ceres. There's sort of a lot of general carbonaceous chondrites that look kind of like Ceres does. In terms of whether you can deliver material from Ceres to the Earth. So like, do we have something in our collection that may be from Ceres and we just don't know? I did some calculations and some other people looked at it, and I think the answer is sort of like, yeah, there might be a couple. So Vesta is in a very good location with a lot of resonances with Jupiter and Saturn that are basically fast-track material from, if material is ejected from its surface, it gets sent into nearer space. Ceres is not in quite as good of a place for that, but there's still some resonances that could move material there. But yeah, nothing we could say definitively.
What's the rotation period on the surface now?
Ceres, I believe, is 9 hours rotation.
Surface temperature.
Oh, surface temperature. Let's see, it's warmer at the equator and cooler at the poles. I think the equatorial temperature, I'm not positive, but I'm thinking it's something like about 200 Kelvin. So what's that? 70 C below freezing. No, actually, it's a little warmer. I think it's maybe on the order of like 30 or so degrees below below freezing.
You expect some sublimation of ice at that temperature?
Ice would definitely supplement it, yeah. Yeah, so that's one of the arguments for why the bright spots probably aren't pure ice, because they would go away within probably decades or centuries. So we'd have to be pretty lucky to catch them when we are. At the poles, it can stay stable for longer, but probably not exposed as bright white ice on the surface.
Can you get a nice spheric out of Ceres but not having molten core at one time?
So if you just like took all of its ingredients, jumbled them together, and let gravity do its thing, probably not. I think the topography would be a bit more rugged than it is. So I think you would have had to have some melting or at least significant warming, so things were gooey enough to kind of get into that nice equilibrium shape.
Okay, let's thank Dave again. And thank you for coming to this month's edition of Space Drafts. If you've answered a trivia question, come up and you can get your prize. And I think the telescope might still be outside if you're interested in seeing the moon. I think there still might be on the moon till 9. And thank you for coming, and hopefully we'll see you next month. Thanks.